The night air over the channel feels like wet steel as the aircraft noses down, blacked out and low, where radar can't easily sort it from the sea clutter. A few minutes earlier, the navigator had been counting the coastline by smell and shape. River mouth, dune line, a darker blot where houses should be sleeping. Now the whole mission compresses into a tight, ugly truth. They are about to land in occupied France to steal a machine that can see. Not a symbol, not a flag, a working radar set, its valves warm, its waveguide tuned, its display still whispering dots and smears that mean aircraft to the men who trust it. By the end of this story, you'll understand how a small raid at Bruneval wasn't bravado, but procurement under fire, how the Allies treated German radar like a captured gearbox, tore it apart for tolerances and failure modes, and then rebuilt the air war around what they learned. The myth people repeat is simple. Commandos took a radar, and that was that. What people get wrong is thinking the steal was the hard part. The hard part was making the theft useful, moving delicate components without breaking alignment, extracting technical knowledge faster than the enemy could change the system, and turning one night's risk into months of operational advantage. The target sits on a cliff, a Würzburg radar site near Bruneval. From the air, it's a pale dish on a darker patch of ground, like a coin left on a table. But the coin is wired into a whole network. It has power conditioning. It has operators trained to read a fuzzy display. It has communication links, procedures, warning chains, and an unglamorous fact that decides whether fighters rise in time. Detection-to-intercept minutes. Exhibit A is the dish itself, precision mechanical engineering masquerading as a simple circle, a parabolic reflector that must hold shape, a mount that must track smoothly, bearings that cannot bind in cold wind, and a drive system that must keep position while the operator sweeps the sky. Exhibit B is the receiver chain, the fragile heart, cavities, waveguides, and components that hate shock, moisture, and rushed handling. If you drop the wrong box, you don't just lose the part. You lose the chance to measure how Germany is actually seeing you. So the raid is designed backward from the engineering. It's not go attack a site. It's land a team close enough to reach the radar fast, overwhelm the defenders without destroying the equipment, strip the crucial sections, and get out before the response arrives. Every minute on the ground increases the chance of reinforcement, but every second saved by brute force increases the chance the gear is smashed or the wrong parts are taken. The planning begins with a question that sounds mundane until you try to answer it. What exactly must be captured? You don't need the dish if you can't replicate the receiver. You don't need a full receiver if you can't understand the pulse characteristics. You need the pieces that reveal frequency, timing, and how the Germans shape their beam, plus any documents, settings notes, or operator habits that don't show up in metal. That's why a radar specialist goes with the raiders. His job is not to shoot, it's to identify the components that matter while bullets are still crossing the air. There's a cold practicality to that role. In a raid, most men measure success in ground taken and enemies routed. Here, success is a crate with the correct modules, intact enough to teach. Bruneval is chosen because the geography offers both a problem and an escape. The site sits near cliffs, hard for a conventional landing, but perfect for parachute insertion and a sea pickup. The extraction method matters. You cannot run stolen radar parts through a long pursuit over land. You cannot load them into a truck and hope. You need a short, violent window, then water. In London, in briefing rooms that smell of cigarette smoke and varnished wood, the raid's timing gets drawn like a factory schedule. Drop time, assembly time, assault time, strip time, withdrawal time, pickup time. And behind all of it, a question that never leaves the paper. What happens if the German response arrives earlier than predicted? Because the site is not isolated, radar exists to summon reaction. If the station has enough time to transmit warning, the very machine you're stealing may be the trigger for the interception that kills you. That's the cruel symmetry. You must silence the eyes before they call the fists. The night of the raid, the parachutes open like pale wounds in the dark. Men hit ground hard because the wind near the cliffs is unpredictable, and because being gentle takes time. Weapons are checked by touch. Gloves hide trembling fingers. Somewhere nearby, the radar dish is still turning, still doing its job, still scanning a sky it assumes is empty. Then the first shots crack, and the site becomes what it always was: a small system of procedures under stress. Sentries look the wrong way. A runner goes down. A signal wire is cut. And the raiders push in with an objective that sounds like sabotage, but is actually acquisition. The radar cabin is a cramped space of equipment, racks, cables, and the smell of warmed insulation. A display face glows faintly. Operators, if they're there, are not villains. They're technicians doing a shift, but the raiders can't afford to treat them like technicians. They are obstacles, and the clock is ruthless. The specialist moves fast, pointing, naming, selecting. Not everything can be taken. Weight matters. Handling matters. Salt air is already a threat. The dish outside could be damaged by stray rounds. The cabin could catch fire. A single ricochet could punch a hole through a component you can't replace. He goes for the receiver and the associated electronics, parts that can be boxed. He looks for waveguide sections, for the magnetron-like components or cavities that define how the set works, for anything that reveals tuning and pulse structure. He grabs documents if they exist, because paper tells you how the Germans think about the system. Calibration steps, fault logs, common failures, the unromantic details. Outside, the dish looms, a huge circle against the sea-black sky. It's easy to imagine the dish as the trophy, but the dish is mostly geometry. The real trophy is how the Germans turn geometry into early warning that holds under weather, under jamming, under fatigue. And that's the spine of this entire story. In the air war, you don't win by being brave once. You win by learning faster than the enemy can adapt. Radar is not a weapon you fire. It's a weapon you schedule. It determines where you allocate fighters, when you light up searchlights, when you scramble, and how you conserve fuel and engines. Fuel is an invisible constraint here. Fighters sitting on the ground are cheap. Fighters in the air are expensive. Every unnecessary scramble burns minutes of engine life, risks accidents, and wastes pilot endurance. Radar makes scrambles selective, and that selectivity is power. The Allies know this. That's why they're willing to risk men to get the internals. They need to understand frequency and beam width because that tells them what altitude bands are safer. They need to know pulse repetition and receiver sensitivity because that tells them what approach paths are less visible. And they need to know how the operators interpret returns because human procedure is part of the system. The assault team holds the perimeter while the stripping continues. This is where the raid turns into a logistics problem. You have pieces of equipment that must be carried over uneven ground, in darkness, under pressure. You can't just take it. You must package it, protect it, move it without dropping it. Keep it dry. Keep it oriented if needed. Even a small bend in a waveguide can ruin a measurement. Then the withdrawal begins, fast, deliberate, ugly. Men move toward the cliffs where the extraction path has been selected. It's not a neat march. It's bundles, shouts, quick counts, and the constant fear of a flare lighting the whole scene. On the coast, boats wait, but boats are not certainty. Sea state matters. Timing matters. Enemy patrols matter. If the pickup is late, the raiders become trapped between the cliff and the response. If it is early, it risks detection. Every plan assumes a narrow corridor where luck and discipline overlap. Here's the second myth people carry: that commando raids are surgical because they're small. The truth is the opposite. Small raids are fragile. One broken radio, one missed landmark, one wrong turn in the dark, one crate dropped, and the whole operation shifts from capture to survive. When the boats finally take them, the sea becomes a different kind of enemy. Salt spray hits metal. Men shield crates with their bodies. Engines cough. The shoreline recedes, and with it the chance to go back for anything forgotten. Back in Britain, the story most people imagine ends. Radar stolen, mission done. But the real work starts on a bench, under lamplight, with careful hands. Engineers unpack the parts like forensic evidence. They measure, map, and compare. They look for design choices. What compromises Germany accepted, what they optimized, what they left vulnerable. They test how the receiver responds to noise. They infer operating frequency. They examine how stable the system is over temperature. They pay attention to connectors and shielding, not because they admire German engineering, but because every detail is a clue about what the radar can and cannot see. And then comes the consequence that makes the raid worth it. Countermeasures become specific. Jamming becomes tuned. Deception becomes believable. Flight profiles become informed rather than guessed. You don't need to jam every radar everywhere if you can jam the important band in the important place at the important time. Perfection wasn't the point. Availability was. Knowing the enemy's eyes well enough to work around them without wasting your own aircraft and crews. But there's a problem that hangs over the bench work like a shadow. The Germans will notice. A raid on a radar site isn't just theft. It's a message. It tells the enemy you care about their sensors. And once they know you care, they will change how the system is guarded, how it is duplicated, how it is improved. So the real race begins. How quickly can Britain turn captured hardware into operational advantage before Germany hardens the network, upgrades the sets, or alters procedure? How many nights can the Allies exploit what they learned before the window closes? The last crates are logged, labeled, and moved deeper into secure rooms. And somewhere in occupied France, German officers walk a damaged site and ask the one question that matters. What exactly did they take? Because the site is no longer just a sensor, it's now a crime scene with a lesson. And Germany's first move will be to tighten the lesson into steel. Within hours, the empty slots in the racks matter as much as the missing men. A radar station is a chain of tolerances. Alignment, power stability, receiver noise, operator technique. When you rip pieces out, you don't just reduce performance, you introduce uncertainty. And in air defense, uncertainty is expensive. It forces more patrols, more false scrambles, more engines run hot for nothing. That is why the German response cannot be repair only. It has to be protect the method. Guards change, perimeters thicken, procedures harden, the radar network which used to be a quiet industrial routine, now has to live like a frontline unit. But the Allies have their own clock, and it is sharper. The first technical interrogation of the captured parts is not romantic. It is a bench, a lamp, a micrometer, and engineers who know that a good idea is useless if you can't reproduce it in time. They are hunting for the practical numbers: frequency band, pulse timing, beam width, receiver sensitivity. How stable the set is when damp air creeps into connectors. How quickly the operator can reacquire a target after clutter. Exhibit A is frequency. If you know the band, you can build countermeasures that are not guesses. Jamming is not make noise. It is inject the right noise in the right place, and do it without broadcasting to every listener that you're blind and scared. A jammer that floods everything wastes power, overheats, and gives away your intent. A jammer that matches the enemy's receiver characteristics can do more with less and stay in the fight longer. Exhibit B is how the Germans interpret returns. A radar display is not a photograph. It's a suggestion. The operator chooses what is real. If the German procedure teaches them to trust a certain smear at a certain range, you can exploit that trust. Not with magic, by shaping the signal so the display lies in a way the human expects. This is where the raid begins to pay off in a way most people never picture. The captured parts become a calibration tool for deception. Engineers can now test, what does the Würzburg receiver do if we feed it this? They can shape pulses, measure response, and build a playbook that anticipates the German station's behavior under pressure. But there's a trap. The Germans will not sit still. The moment they learn the Allies are willing to steal radar, they assume the next move is jamming and spoofing. And once both sides know that, the battlefield becomes a contest of signal discipline. Who can detect the lie and who can hide the lie inside normal noise? So British planners look for something even more valuable than how to jam. They want to know the limits. How much clutter overwhelms the operator? How narrow is the beam really? How quickly can the dish turn and reacquire? How much does the system drift when the wind shakes the mount? These are not trivia. They are constraints that define what is possible over the channel at night when crews are tired and the air is wet. A specific window matters here. Early 1942, when air defense is already an engineered system, not a scattered collection of guns. You have radar early warning, plotting rooms, communications, fighters on readiness, searchlights, and flak. The time from detection to interception is a pipeline. Break any segment and the whole defense lags. Now picture the operational context as a real slice. A coastal sector in northern France on a cloudy night, the radar dish sweeping, the operator leaning in, the plotting phone ringing, and a fighter pair waiting with engines cold to save hours of maintenance. If the radar gives a confident track, those fighters scramble. If it does not, they stay. That decision is made in minutes, and it's made dozens of times a night. The Allies' new advantage is not that they can erase radar. It's that they can start to manipulate the confidence of the track. The easiest myth to sell is the raid blinded Germany. But the radar network does not die from one cut. What changes is the cost of certainty. If Germany has to assume that some returns may be corrupted or ambiguous, they either scramble more, burning fuel and engines, or scramble less, accepting higher risk. Either way, they pay. And the British side pays too, because deception must be delivered through real equipment with real limits. You can't ask a bomber stream to fly a perfect shape if wind drift and navigation errors spread them out. You can't ask a jammer to hold a tone forever if its power valves cook themselves. You can't ask crews to follow an elaborate timing plan if radio discipline breaks down in the dark. So the captured radar becomes a design spec for Allied operations. It informs how you route aircraft. It informs when you add noise and when you stay quiet. It informs whether you fly higher or lower through the beam's geometry. And it pushes the war toward a brutal, technical truth. Survival depends on understanding the enemy's sensors as well as your own engines. But there is another consequence that feels almost unfair. Once you can measure the enemy's radar, you can also measure your own visibility. You can estimate what cross-section features stand out, how formations appear, how altitude changes the return, how sea clutter hides low aircraft. That informs not just jamming, but tactics, approach routes, timing, even the choice of targets. It turns the air war into a system optimization problem, not a contest of courage. Germany senses this drift. They do not need to know every detail of what the Allies learned. They only need to know the direction. So they respond with layers, more camouflage around sites, more decoys, better local defense, and adjustments in procedure that aim to reduce how predictable operators are. Yet procedure is sticky. A radar station is staffed by men trained to do the job one way. You can issue new orders, but you can't instantly rewrite instinct. If the Allies learned a procedure from captured documents or from the very layout of the cabin, Germany cannot erase that learning overnight. That is why the window after Bruneval matters. It is a period where the Allies can exploit a specific understanding of Würzburg before the German system evolves. Exploit does not mean win the war in a week. It means shaving minutes off detection, carving confusion into the warning chain, and buying bomber crews a little more darkness. And this leads to the next forward pull. The Allies have proof of how one German radar works, but they still don't know the whole network, how early warning hands off to tracking, where the weak links are, and what happens when Germany starts changing the parts you didn't capture. And that sealed folder is useless unless someone turns its contents into operational advantage before Germany changes the rules again. So the next step is not another raid, it's calibration, and it happens in rooms that smell like hot dust and ozone from overworked valves. Engineers feed controlled signals into receiver stages, watching how quickly the trace blooms, how it decays, where it smears when the pulse spacing changes. They are not trying to break radar as an abstract concept. They are trying to bend a very specific machine in a very specific way, quietly enough that the enemy mistakes the bend for weather, clutter, operator error, or pure bad luck. Exhibit A is the uncomfortable truth about jamming. It's easy to be loud and hard to be believable. A brute force jammer can announce itself like a siren. The German operator sees the display wash out and knows immediately what's happening. The defense system then adapts in predictable ways. Shift frequency if possible, tighten procedures, rely more on visual confirmation, or switch to alternate sets. Loud jamming can also poison your own side, masking the track data your controllers need. Power is not free, and on an aircraft, it is paid for in weight, heat, and reliability. The Allies need something more surgical. They focus on timing and on trust. If you can create a return that looks like an aircraft at the edge of detection, the operator leans forward and commits. If you can create returns that appear to drift, to split, to merge, you can make a plotting room hesitate. Hesitation is not dramatic. It's a few seconds on a telephone exchange, a controller saying confirm, A fighter pair held one more minute on the ground. But the air war is built out of those minutes. A late scramble means less climb time, fewer options, and a higher chance the intercept becomes a chase you never catch. What people get wrong is thinking deception starts with the aircraft. It starts with the enemy's interpretation of the screen. The raid helps because it reveals how the German set turns electromagnetic reality into human decisions. And now the story narrows to a single operational slice, because this is where the system either works or it doesn't. Picture an RAF planning room in the spring of 1942, late afternoon light fading, with weather reports pinned up and an operations map already crowded with chalk marks. A small group is building a route not just around guns and fighters, but around beams. They know where early warning listens, where tracking can grab, and where the handoff happens. They also know that crews are not perfect. Navigation error is real. Wind drift pushes formations apart. Radio discipline breaks under stress. If a plan depends on perfect shapes, it will fail. So they design for tolerances. They plan a corridor where the beam geometry is less favorable, where the dish must swing farther and reacquire more often. They choose altitudes where clutter is more confusing, but not so low that fuel burn and fatigue ruin the mission. They decide where to spend their limited electronic noise and where to stay silent to avoid tipping their hand. Then when the aircraft are airborne, the clock pressure shifts. Engines do not care about theory. A fighter patrol can only loiter so long before fuel forces a turn home. A bomber stream has only so many minutes to reach its timing gate before the whole choreography breaks. A jammer's power stage runs hotter the longer it is pushed, and overheating leads to failures that are not dramatic. They're just dead boxes. Now Germany is reacting inside its own constraints. Their radar sites sit in weather that corrodes contacts. Their operators work long shifts. Their reporting chain is a pipeline of phones and human voices. When something looks wrong on the screen, the operator has to decide, is it interference? Is it a real track? Or is it a malfunction? If they call it wrong, they either waste fighters or miss the threat. The captured components and layout details from Bruneval change how the Allies bet on those decisions. They can estimate what the operator sees, and that means they can build plans that lean into the enemy's likely habits. But Germany is not passive, and the most dangerous adaptation is not a new gadget. It is a new rulebook. After a shock like Bruneval, the Germans harden not just the perimeter, but the workflow. They can order extra checks, require second confirmations, shift how reports are phrased, reduce the discretion of a single operator. They can introduce redundancy, pairing sites or cross-checking with other sensors. Redundancy improves reliability, but it slows response. In defense, there's a cruel trade. You can be fast or you can be sure. Rarely both. So the British objective becomes sharper, force Germany to choose sure and bleed them of fast. This is also where the raid's psychological effect becomes operational. A radar station that believes it is being targeted behaves differently. Operators become cautious, and caution changes the tempo. Caution also increases fatigue because every ambiguous blip becomes a debate. Fatigue produces errors, and errors look like noise. In a system built on human interpretation, fatigue is a weapon. But there is a second danger for the Allies. Once you rely on deception, you can start believing your own story. A plan that should confuse radar can fail because the atmosphere shifts propagation. A beam can bend. Sea clutter can change with wave state. Equipment drifts. And on the night, the enemy can do something simple. Turn the set off, rotate the dish pattern, or switch to a backup procedure that was never in your captured sample. That is why intelligence teams keep pressing for more than hardware. They want the living network, what radar feeds into, how often it reports, what the plotting rooms do with it, and how decisions are made under stress. The raid gave a window into one node. The operational problem is the whole organism, and this is where the forward pull tightens. If Germany can modify its procedures and perhaps its frequencies, then the Allies must either keep stealing snapshots of the system or find a way to influence the system at scale across many sites without needing to touch each one by hand. And once you realize that, the sealed folder stops being a souvenir and becomes a lever. Because if you can influence how many sites see noise at the same time, you don't need to touch each radar set to change the air picture. The British answer, as the operational reality implies, is to scale the problem the same way Germany scaled its defenses, with a system, not a stunt. They do it by treating the entire coastline as a chain of handoffs. One site detects, another tracks, a plotting room consolidates, a controller decides, a scramble order goes out, and only then do fighters become metal in the air. Every link has delay. Every delay has a range cost because aircraft move fast and fuel is finite. If you can add even small uncertainty at the first links, the later links consume precious minutes trying to recover confidence. Exhibit B is procedure. It sounds boring until you see it under pressure. After Bruneval, Germany's instinct is to harden. They tighten checklists. They require confirmations. They try to cross-check suspicious tracks. And that does improve certainty, but it also slows the machine. Slow means fighters launch later, climb later, and reach the interception box with fewer options. Slow means controllers talk more and act less. Slow means the defense begins to chase the raid instead of meeting it. Now in British rooms, the work shifts from can we see their screen to can we predict their behavior. Engineers and intelligence officers map out the likely defensive reactions and build plans that force the enemy into the wrong choice at the wrong moment. Because there are only a few choices available. Option 1. Treat ambiguous returns as real and scramble often. That burns fuel, hours, and airframes. It also exhausts pilots. Exhaustion is the quiet killer of readiness. It makes landing accidents more likely. It makes navigation sloppier. It makes night flying riskier. And it creates gaps tomorrow, even if you win the argument tonight. Option 2. Treat ambiguous returns as interference and wait. That saves effort, but it risks surprise. The first time a false track turns into bombs, the entire system swings toward panic and overreaction. Option 3. Change the technical parameters, shift frequencies, alter pulse patterns, introduce new filters, or rotate site responsibilities. But technical shifts are limited by production, spares, and training throughput. A coastal network is not one device. It is hundreds of people doing a practice dance. Change the dance too quickly and you fall. That constraint is the beating heart of this story. The raid did not steal Germany's eyes forever. It stole time. Time is what you spend to adapt. And in war, time is the one resource both sides run out of. Here is the anchored moment that shows how it plays out. A coastal station on a damp night, early to mid-war, Europe. The operator has been on watch long enough that the hiss of the set feels like part of his breathing. The scope shows faint, messy returns near the edge of detection. Is it weather? Sea clutter? A real formation riding a corridor where geometry is poor? He calls it up the line. The plotting room asks for confirmation. Another site tries to pick it up. The track is inconsistent, appearing, fading, splitting, rejoining. The operator doesn't know that this is exactly the kind of uncertainty the British now want to manufacture, because uncertainty forces bureaucracy to do what it always does: demand more certainty. While that happens, engines somewhere else are warming. A bomber stream or strike element is ticking through timing gates. Every minute the German system spends trying to be sure, the intercept solution decays. Fighters can still launch, but now they have to burn climb at maximum power to catch up. That consumes fuel they would have used to hunt. The intercept becomes a rushed vector, and rushed vectors miss. That is the mechanism, not magic, not a single clever gadget. A small shove in the early links ripples into a larger failure later, because the whole system is time-coupled. What people get wrong is assuming radar equals certainty. Radar is an instrument, not a verdict. The verdict is made by tired humans following procedures designed for yesterday's problem. But this sword cuts both ways, and the British know it. If they lean too hard on deception, the atmosphere can betray them. Propagation shifts can make a clean plan messy. Equipment drift can make surgical noise leak into their own side. A plan can fail simply because one unit does not hold radio discipline, or because a single box overheats and dies at the worst moment. So they build margins. They design routes that still work if the deception is weaker than hoped. They train crews to fly to simple, repeatable cues. They keep the technical effort focused on what matters most, forcing the defense to hesitate at the exact moment hesitation is most expensive. This is also where the Bruneval raid's legacy becomes clear. It is not that it revealed a secret bolt or a mystical frequency. It revealed a living interface between machine and mind. It showed how the Germans saw the world, and that meant the Allies could begin to write fiction into the enemy's perception. Just plausible enough to be acted on, and just uncertain enough to trigger delay. And it hints at the larger pattern you can watch across the war. The side that wins is often the side that manages systems better, not the side that owns the single best component. Perfection wasn't the point. Availability was. By the time Germany adapts with new rules and patched hardware, the Allies have already banked the real profit. They learned to move inside the enemy's decision cycle. They learned how long it takes a report to become an order, how long it takes an order to become wheels up, and how long wheels up must have to become an intercept. That's the true theft. Not eyes, but minutes. And once minutes are stolen repeatedly, even a powerful defense starts to feel like it's always arriving late, always reacting, never shaping. Thanks for watching. If you want more World War II stories told through real constraints and mechanisms, subscribe. Link is in the description.